All right, so our next speaker is Pascal Oesch, who's going to tell us about Fresco.
Okay, hello everyone. Yeah, it's really an amazing privilege to be talking to you as one of the PIs of a Cycle 1 James Webb program. And in my case, this is Fresco. This is a 53-hour medium program of NIRCam GRISM spectroscopy at 4 to 5 micron. So Fresco will be conducted by a team of about 25 scientists all around the world, really. You can see their names listed here. We're all experts in galaxy evolution, from imaging and spectroscopy, but especially also we have a strong expertise with HST GRISM spectra, which is going to be important for this program. But really, the Fresco is also intended as a legacy program for the community. We'll be imaging the Candle's deep fields, which are, of course, are really prime extragalactic fields, and the data will be public immediately, so you can play with it as soon as they get off the telescope. And so I'll just show you some of the science that will be enabled by Fresco in this talk today. Just very quickly on one slide on motivation, really for me, the key motivation here is that, well, as you know, with Hubble, we have been collecting huge samples of galaxies in the epoch of ionization, redshift 6 and above, from photometric techniques. However, only a very minor part, 1% only also of the sources at redshift above 6 do have a spectroscopically confirmed redshift. And so this really severely limits our physical interpretation of these sources, right? With photo Z uncertainties reaching up to delta Z of 0.5. I mean, we have limited accuracy with which we can determine physical parameters like stellar masses of these sources. We don't know anything about the 3D distribution of these sources, and we don't know anything about their contaminants in a sense. And so that's really the main motivation. And how can we overcome this? Well, we know that these sources at redshift 7 and above have extreme rest frame optical emission lines. And we know this from Spitzer. If you look at the Spitzer imaging of some of these sources, you can see that they're really booming in IRAC. And it's been known for a while that this can be only explained, really, if you look at the IRAC colors of sources, redshift 7, redshift 8, they're very different, and you can explain this only through very strong rest frame optical lines, O3 and H beta, that are shifting through these two filters. And so on average, we can determine that these equivalent widths are rest frame 700 angstroms. And as you can imagine, and as you can also see here in this SCD, this really has well, bad implications in the sense that we have large uncertainties on the stellar masses of these sources, even with James Webb imaging in the most extreme cases of a factor 5 to even to 10. But yeah, these lines are extremely strong, as you can also see here in this equivalent width distribution plot. And so we can now, with Fresco, exploit these strong lines and use James Webb's unique spectroscopic window that is being opened up to get an emission line select galaxy sample during the epoch of ionization and remedy this situation. So how are we going to do this? Well, we're using slitless spectroscopy. So we're using NIRCam, as I said. We're taking a direct image here. This is a simulation that Gabe Bremer did for us from the Hubble Ultra Deep Field. This is the F444W direct image, and then you put in the GRISM, and as Casey was showing earlier, right, you just essentially smear out this whole image, and you get essentially a spectrum for every single galaxy in the field, but because it's slitless, they're also overlapping. So we'll get back to that. But as you zoom in on the trace of a redshift 7 source, you can see here very clearly we will be able to get, so these spectra are of 1600, so you can split the O3 doublet, also H beta, and so we can really ambiguously select these sources through their emission lines, yeah, through these 3 emission lines. H beta here in this case is somewhat faint, of course. And so just to give you an overview of the survey design of Fresco, as I said, we're targeting the Candle's deep areas. So these are the central pointings in Good South and Good North. So we'll be doing 2 times 4 mosaics. So in total, we will get 120 square arc minutes of GRISM spectroscopy. And so in particular, we're using this F444W filter for a 2-hour GRISM spectra. And as I said, we also need very short direct images to identify the position of these sources. And then the really cool thing about NIRCam is that you can observe in the long wavelength channel, and at the same time, you can observe in the short wavelength channel. And in our case, we're performing imaging in medium band filters, F182M and F210M, so 1.8 and 1.2 micron. And that really extends the candles data that is available already in these fields from HSV and also complements the GTO JADES data. So in terms of depth, with the F444W GRISM spectra, we will cover 3.9 to 4.9 micron with a line sensitivity of about 3 times 10 to the minus 18 ergs per second per centimeter squared at 6 sigma. And so we expect to detect essentially the O35007 flux for sources about 1 magnitude below L star. Then in terms of imaging sensitivity, we will expect a 28.5 sigma for a point source in the medium bands, and as I said, relatively shallow in 444W. And so in total, the survey requires 53 hours, again, medium program with 36 hours of science time. And again, important, the data are public immediately. So you can expect, we have observing windows between October, December for Good South and January, April for Good North. And the actual orientation of these pointings will also depend a bit on the scheduling. Just a quick word on advantages and disadvantages of slitless spectroscopy. As you've seen, right, we obtain a spectrum of every single source in the field, which is great because it allows us to get a complete emission line selected galaxy sample, which really is impossible to achieve with NIRSpec, both because you have to pre-select sources, but also because of the fixed grid of the MSA. And then we will obtain total emission line fluxes. So we will be able to get slit loss calibrations for MSA spectra from our data in the same field. But the main problem here, of course, is that we really do need to model the spectrum of every single source in the field to be able to clean for contamination. And because of the very large overheads, we are only taking one orientation. However, we can build on our extensive experience with HSD GRISM surveys, like 3D HSD, for instance, and in particular, we will be building on this amazing software tool that Kate Bremer has written, Grizzly, that is really built for space-based slitless spectroscopy. And you can find this on GitHub already. And so what's the science that this data will enable for the epoch of ionization, which is, again, important for the conference here. You can see here on the left, we will be able to really get spectroscopic redshifts for a large number of sources at a high redshift. So we expect about 330 spectroscopic redshifts from redshift 7 to 9. You can see down to the absolute magnitude limit that we expect this. And even at lower redshift, we expect about 1200 redshifts from redshift 5 to 6.5 through the H alpha line, for instance. And so this will allow us to really probe the 3D, the small scale clustering of sources, and really the buildup of the galaxy population and ionized bubbles and so on in these two fields. Then on the other hand, we will get these terrestrial optical spectra for sources. These terrestrial optical emission lines that we can then really, on a source-by-source basis, subtract these emission lines from the broadband photometry. Here this is Spitzer photometry in this case, but really get accurate stellar masses for every single galaxy in this field. And so this will enable UV luminosity functions from spectroscopic samples, accurate stellar mass functions, as I said, but it will also allow us to get the 3D clustering as well as ionizing conditions in these early sources and much more. With our 4 to 5 micron spectra, we will not only be able to target high redshift emission lines, but also the Paschen lines that were just asked about earlier, in particular Paschen alpha and Paschen beta, between redshift 1.5 and about 3. And so those will be dust insensitive probes, of course, of star formation. And here's a simulation again of a source in the Hubble Ultra Deep Field, redshift 1.5. Again, if we zoom in on this source, we can directly get an emission line map, the Paschen alpha map. And so really that gives us the spatial distribution of star formation. And again, in terms of science, we can really probe that we get dust insensitive probes of inside out versus outside in growth of galaxies really across cosmic history, because of course we can also do this with H alpha and at higher redshift as well. Then just a quick word on the imaging. We will, as I said, we get these medium band images here around 1.8 and 2.1 micron, and that really extends what is available in these fields with Hubble. So essentially everything, all the science that can be done with Hubble, we can extend to slightly higher redshift. In particular, Balmer break studies, also identifying quiescent galaxies in these fields up to higher redshift. But also we get UV continuum slope estimates directly for the sources for which we will get redshifts from the GRISM spectra. And so just the data products to finish up. Again, we'll be following the very successful data release model of the 3D HST survey. So you can expect to get 2D, 1D calibrated spectra, of course, catalogs of redshifts, but also emission line measurements, the 2D emission line maps for sources that are well detected, and of course, these NIRCam images that are aligned and calibrated to the CANDLE's deep data, in particular the medium band filters. And finally, we will also photometric catalogs that include physical parameters that are derived after correcting for this emission line contamination. And importantly, I think we will also really be able to provide statistical correction factors for emission line contamination in broadband photometry that can be used in other surveys that are being conducted with James Webb all over here. And so this I just leave up my summary of FRESCO. Again, it's a NIRCam GRISM survey, and you can get news in this webpage that is still under construction. Thank you very much.
Thank you very much, Pascal. I can see there's a couple of questions already in the Slack, but we'll give people 30 seconds or so just to add some extra ones. Oh, just while waiting for a couple of extra questions, when people are interacting via Slack, we kind of think it's a good idea whether people can rename themselves with their full name, but also their institution, perhaps your pronouns, and also your career stage, just to help with your interactions between researchers at different levels. So I think if you should be able to see a few of the SOC have adopted this already. We just think that would be really useful. Steve, do you want to ask the first question?
Yeah, Pascal. So the first question is, what could we learn from stacking the spectra of the high redshift galaxies? Could we measure metallicities at redshift greater than 7?
That's, yeah, very good question. That's definitely something we would like to do. We will get H alpha here and then 2 as well, of course, for redshift 5 to 6.5 redshifts. Well, in principle, unfortunately, we only have this very limited window, right, of from 4 to 5 micron. So in most cases, we only get the one line, but definitely we will be trying to model this, also the O3 and H beta lines, and hopefully get some information about the metallicity build-up as well.
Thanks, Pascal. Another question asks, how much of a gain would you make by adding a second orientation, perhaps in cycle 2? Presumably it wouldn't just be kind of doubling the amount of data you've got, because it hopefully makes subtraction. Sorry, I'm kind of paraphrasing this to add a bit more detail.
Yeah. No, I mean, the problem is really with the overheads. So essentially, if we added the second orientation, we would have added essentially 15 hours of overheads without any gain in sensitivity, right? And the main problem is what you see here, right? With 3D HST, for instance, we also have only one orientation. We have to model all the spectra, and it's really only kind of a gain is only in systematics in a sense. And if you're really interested in one particular galaxy, then a different orientation might be very useful. But in a statistical sense, I think we will have a good handle on these sources, and we will be able to subtract and model the contamination quite well, I think.
Thanks, Pascal.
I'll ask one more brief one, if that's okay. So a couple different versions of this question, but do you expect line emitters that lack continuum detection either in the existing HST imaging or in your direct imaging, or presumably in the JADES imaging in the field?
Yeah, that's a very good question. We don't know. Let me go back to the equivalent with distribution plot from Ryan here. We don't know what's going on up here, right, at the very high end of this O3 and H beta equivalent with distribution plot. but at least for a source that has an average terrestrial optical equivalent width of about 700 angstroms, we specifically designed our pre-imaging, which is really shallow, right, to be able to detect every single source that has an O3 and H beta line. But indeed, there may be sources out there that with much stronger lines that we will have to hunt out, maybe in the JADES data when they become public.
Thank you very much, Pascal.